Hey guys. So in this lesson, we're going to kind of go back to limits, which was the very first chapter that we did. And in that chapter, what we never did was have the limit as x goes out to infinity or as x goes to negative infinity. And that's what this whole lesson is all about. When we did limits, it was as x approaches 2, or as x approaches 4 from the left, or as x approaches 6 from the right. But now it's what happens if x gets really, really big? What is the y value approaching? Or as x gets really big in the negative direction, what's the y value approaching? You've already done this topic in Algebra 2 and in Pre-Cal, just now we're putting different notation to it. And let me explain what I mean by that. I'm going to kind of skip this opener right here and this thing right here. And I hope that's okay with you guys. But in general, here's what I'm saying. If you have a graph, okay, you don't need to write this. But you have a graph, and it looks something like this. And I say, what's this y value approaching as x gets way, way out here? Well, you could see this graph is leveling off, and the question is, what y value is it leveling off at? Otherwise known as, what's the horizontal asymptote of this function? So anytime a question says, find the limit as x goes to infinity, as you could see right here, the question is basically saying, what is the horizontal asymptote of this function? And when you had Algebra 2 and when you had Pre-Cal, you learn these horizontal asymptote rules, and those rules are going to come back again, okay? And so we're just going to jump into these examples. Actually, before I start, I just want you to think about this. If I had the limit as x goes to infinity of 2 over x, I want you to think about what this would get closer and closer and closer to, okay, which is really kind of a big part of the lesson. So you can't technically plug infinity in for x, right? But you could think about what happens as this denominator gets bigger, 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 as big as it possibly can, getting closer to infinity. Think about what this fraction is getting closer and closer to. Well, if you had 2 over like 100 million trillion quadrillion, I don't even know if that's a number, but that fraction is going to get closer and closer to 0. Right there. That's going to get closer and closer to 0. And that's kind of the idea of today. So I go to example 1, and it says, find the limit of this function as x goes to infinity. And if you think back to our limit properties, this was a long time ago, but one of the properties said you could split up a limit expression into two separate limits that are being added or subtracted. So like I could write this as the limit of 5 as x goes to infinity minus the limit of 2 over x squared as x goes to infinity. So basically I'm splitting this up into two separate limits. Well, again, if you think back to our limit stuff, the limit of a constant, think about graphing the line y equals 5. That's what this first one's saying. Well, as x gets really, really big, the y value is always going to be 5. So that first limit is just 5. And then the second one, as the denominator gets bigger, 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 then 2 divided by some giant number, this is getting really close to 0. So we have 5 minus 0, which is 5. Now, if you think back to horizontal asymptote rules, because that's really what we are applying to here. This is where example 3 comes into play. So think about your horizontal asymptote rules. If I see the limit as x going to infinity, then in my mind, I'm thinking, okay, what's the horizontal asymptote of this function? If I would sketch this graph, what's the horizontal asymptote? Whatever that is, that's the answer. And there's pretty much 2 rules to keep in mind as a refresher. Anytime you have the same degree on the top and bottom of your expression, so like here I have x to the first and x to the first, then your horizontal asymptote is just whatever the leading coefficient fraction would be. So instead of doing any sort of algebra, there's some manipulation you can do, but I don't teach it anymore because it doesn't, I don't think it actually helps. But if I think, what's the horizontal asymptote of this function? Well, when the degrees are the same, then it's just the leading coefficient fraction. This would be getting closer and closer to 2/3 right here. And the reason it is, let's say you're taking a quiz or test or whatever, and this comes up, Well, yeah, you can't technically plug in infinity, but as x is getting gigantic, this 3 and this 1 are pretty much non-existent. And so then you're getting 2 times a giant number over 3 times that same giant number, and that fraction is going to reduce to 2/3. And that's what's happening with this horizontal asymptote rule. All right. So if the degrees are the same, it's the leading coefficient fraction. If the bottom degree is bigger, well, I like to think about in terms of dominating, right? So if the bottom is squared and the top is x to the first, well, think about what happens if you plug in some gigantic number for x. They're both going to go to infinity, right? If I plug in, I would use air quotes if you could see me, but if I plug infinity into both these x's, I'm going to get infinity on top and on bottom. But there are various degrees of infinity. The bottom is going to grow so much more quickly compared to the numerator. When you square a giant number, it gets so big compared to the top. And so you relatively have a small number over a big number. Even though they're both really big, if I plug in 100 million, they're both big, but 100 million squared in the denominator is so much bigger. So yeah, you have a big number on top, but you have a big number on bottom. And so that fraction is getting closer and closer to 0, which is what your limit would be. And the second horizontal asymptote rule is if your bottom degree is bigger than the top degree, then your horizontal asymptote is 0. So you can just look at it in terms of your horizontal asymptote rules. And then the last thing, if the top is bigger than the bottom, then there is no horizontal asymptote. Your limit would be does not exist. So this are kind of the few things that could happen. Your degrees are either the same, in which case it's the leading fraction. Your bottom degree is bigger, in which case it's 0. Or your top is bigger, in which case it does not exist. There are a few other things, though, because they're not always just going to be polynomial fractions. Enter this problem here. So this one's going to be a little bit different, and I've kind of learned how to teach this one. What I've learned is these problems, as x goes to infinity and negative infinity, these are not free response questions. These are typically multiple choice questions. What I mean by that is the work doesn't really matter so much. On multiple choice, you just have to have a way to get to the answer. And that's what happens here. So if I have this first fraction, as x is going to infinity, okay? Well, if x is getting really big, then this 3 doesn't really matter at all. And this 1 on bottom really doesn't matter at all. In the grand scheme of things, the 3 and the 1 are pretty much non-existent. Okay. On bottom, I have square root of x squared. And if you were in class, I would say, hey, what's the square root of x squared? And a lot of students would say x. And that's technically wrong. The square root of x squared is not x. And I want to talk about why really quick. If you say this equals x, and then I ask the question, I say, okay, what's the square root of negative 3 squared? Well, if your top rule is correct, then the answer to this question would have to be negative 3. X is negative 3. But that's not right, because this is the square root of 9, so it'd be positive 3. So this rule isn't right, and the way we fix it, the square root of x squared is technically the absolute value of x. It's the positive of whatever x is. Okay, so bear with me on this problem. So that means I have the limit as x goes to infinity of 4x over, and then I have the absolute value of x on bottom, right? And now think about what happens as x gets really, really big. Well, if I plug in a million, for instance, I would have 4 million over 1 million, which is 4. If I plug in a trillion, I would have 4 trillion over 1 trillion, which is 4. And so basically this limit is always going to be getting closer and closer to 4. So mathematically, is that notation, good? No, not really. But being a multiple choice question, we just have to have a way to get to the answer. and that's how we can do it. Now notice on the next one, it's approaching negative infinity, but we're going to apply the same idea. This one's a little bit different. So I would have the limit as x approaches negative infinity of 4x over the absolute value of x. Okay, well now think about plugging in giant negative numbers. I know a million's not gigantic, but let's say I plug in negative a million. So I would have negative 4 million on top. On bottom, if I plug in negative a million, that would become positive 1 million. And so basically, this is always going to become negative 4, because the top will always be negative and the bottom will always be positive. This is just a weird type of problem. When you're square rooting x squareds, it becomes absolute value of x, and then just think about what that fraction would reduce to. But essentially, conceptually, you're just getting rid of all the other stuff. Like the 3 and the 1 really meant absolutely nothing in the grand scheme of things. So just get rid of them. All right, last couple. So with trig, a little bit different to think about. So if I want to find the limit of sine of x as x goes to infinity, well, let's think about what that graph would be approaching, getting closer and closer to. Well, think about what the sine graph looks like. Starts here and it goes, oh no, that was cosine. Oh shoot, that was silly. Starts here at the origin. I mean, it looks the same eventually, but you know, I don't want to mess anyone up. And just keeps going, oscillating. So as x is, that's a terrible sine wave, but as x is getting really, really big, this graph, the y values are not getting closer and closer to anything. They keep just changing, and so the limit of this one does not exist. So there's not really a horizontal asymptote rule to apply. We just need to think about it. Same thing on the next one. The limit of sine of x over x as x goes to infinity. Okay, well, think about what's happening. On top, if you take sine of anything, think about that sine graph I just showed you. The biggest the y value will ever be is 1, and the smallest the y value will ever be is negative 1. Sine goes between negative 1 and 1. That means no matter where you are, no matter what I plug in for x, this value on top will always be between negative 1 and 1, a really small number. On bottom, however, if I'm going out to infinity, the bottom is getting huge, getting gigantic on bottom. So on top, you just have a number between negative 1 and 1, some really small number. The bottom's getting gigantic, and so a small number over a gigantic number is getting closer and closer to 0. So you're not really applying horizontal asymptote rules there, but just kind of thinking through what's happening. All right, and then at the bottom here, I just have a little refresher on your horizontal asymptote rules. If the degree of the numerator is less than the denominator, so if the bottom is bigger, then it's 0. If the degrees are the same, it's the leading fraction. And if the degree of the top is bigger than the bottom, then the limit does not exist. All right, let me know if you have any questions. Peace.